Okay, so last time we derived the first law of thermodynamics, in other words, conservation of energy equation for a control volume. From this moment on, before you use first law of thermodynamics, the first thing you have to do is to find out if your system is a closed system or a control volume. If your system is a closed system, you need to use the short version of first law, which is Q minus W equal to delta E. If your system is a control volume, you have to use the long version of first law, which is the one in this box. Okay, so now we have one example. In this example, we have a nozzle and it's insulated. What a nozzle does is to increase the fluid velocity. Here the nozzle has a converging shape. And you see the short lines on the lateral surface of this nozzle. Those short lines mean it's insulated. Okay, and we know the substance is H2O. Pressure of the fluid at inlet is 40 bar. Temperature of the fluid at inlet is 400 Celsius. Velocity V1 at inlet is 10 meter per second. And at the exit, P2 is 15 bar and V2 is 665 meter per second. Much bigger. We also know the system is at steady state. Mass flow rate m dot is equal to 2 kilogram per second. We're looking for three things. The first one is the specific enthalpy H2 at the exit. Second one is to sketch this process on P versus nu and a T versus nu diagrams. And the last one is to look for the cross-sectional area of surface number 2, A2. Let's start from the first one. Okay, we're probably going to use first law of thermodynamics because that's the only equation we have that has H in it. Okay, so now what we're going to do is we're going to identify if our system is a closed system or a control volume. So from the setup, we can easily tell it must be a control volume because you have inlet and outlet. So let's copy down the first law for a control volume, which is Q dot minus W dot control volume plus M dot I, we can use a sigma, and then HI plus 1 over 2 VI squared plus GZI minus sigma M dot E HE plus 1 over 2 VE squared plus GZE equal to right hand side dE over dt. Okay, so this is the original first law for a control volume. And next, we can further simplify this equation. First of all, this nozzle is insulated, so that means there's no heat transfer. If there's no heat transfer, Q dot goes to 0. And next one, W dot CV. Do you remember what W dot CV means? W dot CV, like we said in this box, W dot CV comes from moving parts of your system. Okay, let's take a look. Does this system have any moving parts? Does the control volume push anything or gets pushed? Not at all. So there's no moving parts, so W dot CV goes to 0. Okay, the reason here is no moving parts. And then there's one more thing we can do, that is steady state. Nothing changes over time. Right hand side goes to 0. The reason is steady state. Okay, so now we can simplify this equation. Because this system only has one inlet and one outlet, so there's no need for us to use sigma. And then because for inlet we use number 1, we change subscript I to 1. And for exit we use number 2, so we change subscript E to 2. So this equation becomes m dot times h1 plus 1 over 2 v1 squared plus gz1 equal to m dot multiplied by h2 plus 1 over 2 v2 squared plus gz2. And I didn't give mass flow rate a subscript. Why? Because we know the system is at steady state, so mass flow rate at inlet m.1 must be equal to the mass flow rate at exit m.2. If they're equal, there's no need to give them a subscript. Okay, mass flow rate is the same, so we can cancel them. What is left is h1 plus 1 over 2 v1 squared plus gz1 equal to H2 plus 1 over 2 V2 squared plus GZ2. And next, we can cancel GZ1 and GZ2. Why? Because Z1 and Z2 are the same. Z is the height. So let's say, for example, this is the ground. This is the ground. Where's Z1? Z1 is here, and Z2 will be here. You can see Z1, the height is equal to Z2, the height at the exit. So cancel out Z1 and Z2. And then the only thing we have left is H1 plus 1 over 2 V1 squared is equal to H2 plus 1 over 2 V2 squared. Because we're looking for H2, so we move H2 alone to the left-hand side. And H2 is equal to H1 plus 1 over 2 V1 squared minus 1 over 2 V2 squared. Okay, very good. So as long as we can find everything on the right-hand side, we can find H2. V1, V2, they are directly given. V1 is 10 meter per second, V2 is 665 meter per second. And H1, we don't have H1, so we have to find H1. H is specific enthalpy, which is a property. Like we said before, if you look for a property, the first thing you need to do is to find out what's the phase of the substance. And based on the phase, you make a plan. Okay, so now how do we decide what's the phase of point number 1? Okay, we can take a look at what we know about number 1. We know P1, 40 bar, and we know T1, which is 400 Celsius. From those two numbers, actually, we can find out what's the phase of number 1. We've done this method before, but just in case you forgot, let's do it again. You can go to the table, and it should be table A3 because we're going to start from pressure. We start pressure equal to 40 bar, and then we look for the corresponding saturation temperature, which is like the boiling temperature. And if my actual temperature is even higher than the boiling temperature, which we call saturated temperature in this class, what does that mean? That means your substance must be at superheated state. Okay, so if your actual temperature is higher than the saturated temperature, then your substance must be at superheated state. Okay, so now let's see if this is true for this problem. And like we said, we're going to go to table A3 because it is water, and we're going to start from pressure. P1 is equal to 40 bar. We go to table A3 and start from 40 bar. We look for the saturation temperature. Okay, so let's go to table A3. Okay, don't forget when to use table A2. You use table A2 when you start from temperature. Okay, so we use table A3 because we're going to start from pressure. The pressure we have is 40 bar, right? Remember, the first column is pressure, second column is saturated temperature. Okay, so the pressure we have is 40 bar. We look for 40. So the corresponding saturated temperature at 40 bar is 250.4, and the unit is Celsius. Okay, so now we go back to our notes and write down the saturated temperature. At 40 bar, we found the saturated temperature at this corresponding pressure is equal to 250.4 Celsius. Okay, and what is my actual temperature at number 1? My actual temperature at number 1 is 400 Celsius given by the problem. And now you can see your actual temperature is even higher than the saturated temperature. So our conclusion is point 1 must be superheated. Okay, so now we know the phase of number 1 is superheated. What's your plan to look for H1? Remember, if you look for a property of a superheated water vapor, then you have to use table A4. So now we made our plan. Because we know the phase is superheated, so we know we have to go to table A4. Okay, and remember, if you want to use table A4, you have to use two inputs, and then one of the inputs has to be pressure. So do we know anything about H1? Yes, we do know the pressure, which is our first input for number one, 40 bar. What is the second input? We know about point number one. The second input we know is the temperature. The temperature we know for number one is 400 Celsius. And then we go to the table, you can look for the corresponding H, and that will be our H1. Okay, so now let's go to the table. And because it's superheated, we know we have go to table A4. Okay, so this is table A4 for superheated water vapor. And then you can see each pressure has one block for itself. The pressure we have is 40 bar, so we look for 40 bar. Okay, very good. So 40 bar is right here. And then the second input we know is temperature. Temperature is the first column. Temperature we have is 400 Celsius. So we start from 400 Celsius. And then you can find everything at 400 Celsius. The one we're looking for is specific enthalpy, H. And be careful here, the unit this table uses is kilojoule per kilogram. So H1 will be, we can easily find it now, that is 3213.6, and don't forget a unit, kilojoule per kilogram. And then even though I'm not looking for other properties, what I usually do is to also write down as many other properties as possible. So later on, I don't have to go back to the same table and look for those properties just in case I need them. Okay, so what I suggest you do is always write down as many properties as you can, even though you're not looking for that many at the moment. Okay, so the other property I'm going to write down is new. The second column is new, so the corresponding new is 0.07341. And do not forget a unit, cubic meter per kilogram. Okay, so now we go to our table and write down those two properties. H1 is 3213.6 kilojoule per kilogram. And then I also write down specific volume, new one, which is 0.07341 cubic meter per kilogram. So now let's go back to our equation regarding H2. Do we have everything in the right hand side now? Yes, I have everything in the right hand side. So I can easily find H2. Okay, let's copy down this equation. H2 is equal to H1 plus 1 over 2 V1 squared minus 1 over 2 V2 squared. Okay, so plugging H1, 3213.6, and be careful here, it's not in SI unit because it's given in kilojoule per kilogram. So multiply by 1000 to convert kilojoule to joule. Okay, plus 1 over 2 V1 squared. V1 is given as 10 meter per second SI unit, that's good, minus 1 over 2 times V2 squared. V2 is given as 665 meter per second squared. Okay, so our final solution is 2992.5 times 10 to the third. Because I used SI unit for everything, then my solution must also have an SI unit. SI unit for specific enthalpy is joule per kilogram. And then we do one more step, 2992.5, and convert it to kilojoule per kilogram. So now this is H2. This is the solution to part 1, H2. Okay, next one, part 2. Sketch this process on P versus nu and a T versus nu diagram. Okay, so let's do that. Pressure versus nu, temperature versus nu. The first thing we always sketch is the vapor dome. Okay, we sketch the vapor dome. And then remember on P versus nu diagram, we have something called constant pressure line. How to sketch a constant pressure line? Curve down. Oh, sorry. And then go straight. and then curve down again. Okay, so this line represents a temperature. How many constant temperature lines you think we should have? Probably two. One for T1, the other one for T2. So we're going to sketch another one. And this line will be used to represent the other temperature. Okay, so next question. Which line should we use to represent T1 and which line should we should use to represent T2? The rule is the higher this line is, the higher the temperature it represents. So which one is higher, T1 or T2? T1 is given 400 Celsius. So what's going to happen to T2, the final temperature? Remember, this is a nozzle. What a nozzle does is to increase the velocity of the fluid. So what we know is kinetic energy in this process will go up, but we also know energy is always conserved. So if kinetic energy goes up, something else must go down. So what goes down? Pressure will go down, and the temperature will also go down. So T1 must be higher than the final temperature T2. So the top one should be T1 and the bottom one should be T2. Okay, all right. And then where do we locate point 1? Where do we locate number 1? Okay, so we know point number 1 must be on T1 line. And then where do we put point 1? In other words, what's the phase of number 1? What's the phase of number 1? We already proved it. Point 1 must be superheated. So where do we put point 1? On T1 line and to the right side of the vapor dome. So I must put number 1 somewhere here. Okay, so this is how you locate point number 1. Next, how do we locate number 2? How do we locate number 2? So we know point number 2 must be on T2 line. And where do we put number 2? In other words, what's the phase of number 2? Is it possible for us to find what's the phase of number 2? We've used this method before, not exactly the same, but very similar. For example, can you recall we gave you the actual specific internal energy, U, and then you use U, compare this value to UF and UG. If your actual U is between UF and UG, and then we say it must be a mixture. If your actual U is even higher than UG, that means the substance must be at superheated state. Okay, so actually what we can do is the same, but instead of specific internal energy, lowercase u, we're going to use lowercase h because we have H2. So what we're going to do is to compare H2 with H2F and H2G. If H2 is between H2F and H2G, it must be between F point and G point. In other words, a mixture. If H2 is even higher than H2G, has more energy than G point, then that means number 2 must be superheated. Okay, so now what we need is to find H2F and H2G. How do we look for H2F, H2G? Anything about F point or G point can be found in table A2 or A3, depending on what the input is. If the input is pressure, you use table A3. So we do know pressure P2. P2 is 15 bar. So we go to table A3 because we start from pressure. And like we said, we're gonna look for H2F and H2G in the table. The subscript 2 means it's at P2. Okay, so now let's go to table A3. And this time we start from pressure 15 bar. Okay, this table A3 and 15 bar. Where's 15 bar? 15 bar is right here. This is 15 bar. Okay, so first column is pressure, 15 bar. Second column is the saturated temperature. And where is HF and HG? Let's go all the way to the right, HF and HG. Okay, so now we can look for HF and HG. Where's HF? HF is here. This is where HF is, 844.84. And do not forget the unit. The unit is kilojoule per kilogram. And then what is Hg? Which column is Hg? Here, 2792.2. kilojoule per kilogram. This is column Hg. And do not make the mistake by going to HFG when you look for Hg. Okay, HFG, what does it mean? HFG is the difference between Hg and HAF. In other words, HFG is equal to Hg minus HF. Okay, so now we can copy down HF and Hg for our problem. Okay, we'll copy down those two numbers. HF 844.84 kilojoule per kilogram. Do not forget to write the units. Hg 2792.2 kilojoule per kilogram. That's H2F and H2G. And what is H2, by the way? Let's go back. H2 is 2992.5. So which one's bigger? Our conclusion is H2 is even bigger than H2G. Point number 2 has more energy than saturated vapor, so that means point 2 must be superheated. Okay, so now we know point number 2 must be superheated. Okay, and then where do we point number 2? Okay, we know number 2 must be on T2 line and also superheated, so to the right side of the vapor dome. So can I actually put number 2 here, for example here, and then 1 to 2 can be somewhere like vertical or to the left. To make it more obvious, I'm gonna move number 1 further to the right. So for example, if number 1 is here, superheated and on T1 line, can I actually put number 2 here? So when I connect 1 and 2, it's going to be skewed to the left. Or can I put number 2 somewhere here? So when I connect 1 and 2, it's going to be a vertical line. Or can I put number 2 to the right a little bit? So when I connect 1 and 2, they are skewed to the right. So now you can see even we know point 2 is superheated, we still have 3 possible solutions. So we have to identify which one out of the 3 is the correct one. First option 1 to 2 to the left. Second option 1 to 2 vertical. Third option 1 to 2 to the right. So to the left, vertical, or to the right. How do you decide? You compare what? You compare the x-coordinate. If the x-coordinate is becoming bigger, that means the line must be skewed to the right. If the x-coordinate doesn't change, then it must be a vertical line. If the x-coordinate becomes smaller, then this line must be skewed to the left. Okay, so what is the x-coordinate? For our case, the x-coordinate is nu. So what we need is to compare nu1 with nu2. If nu1 is equal to nu2, then 1 to 2 must be a vertical line. If nu1 is less than nu2, then this line must be to the right. If nu1 is greater than nu2, then this line must be to the left. So we just need to find nu1 and nu2. Did we find nu1 already? Yes, we did. Okay, we found nu1 here already, 0.07. And next, we just need to find nu2. Okay, do you remember how you find nu2? The first nu2 is a property of point 2, and point 2 is a superheated water vapor. If you look for a property for superheated water vapor, you have to use table A4. You have to use table A4. And how do we use table A4? Do you remember? You have to have 2 inputs. One of them has to be pressure. P2 is given 15 bar. And then second input, what else do we know about number 2? Do we know T2? No, we do not. But we do know another property about number 2, that is H2. We found H2, and that is 299, 2.5 kilojoule per kilogram. Okay, and from here, we can look for the corresponding nu. Alright, so now let's go to the table. Table A4 this time. And the pressure we know is 15 bar. So we go to 15 bar. Okay, 15 bar is right here. That's where 15 bar is. Okay, and the second input we have is H. Which column is H? Take a look. Second input is H, which is the third column. Okay, so we look at the third column, and the one we have, H2 is 2992.5. 2992.5. We don't have exactly that number, but 2992.5 is between those two numbers. Okay, so what are we looking for? We're looking for a specific volume, first column. So the specific volume we want must be between 0.483 and 0.1627. Okay, so now obviously we have to do what? Interpolation again. Okay, we do interpolation. All right, so we went to the table and we found those four corresponding numbers, new and enthalpy. We can write down those four numbers, 2899.3, 2992.7, 0.14383, 0.1627. We found those four numbers in the table, and the H we have is 2992.5. So what is the corresponding mu interpolation? Okay, we've done interpolation several times now, so interpolation nu2 is 0.1627 cubic meter per kilogram SI unit. So now I found nu2. Okay, let's recall what is nu1. Nu1 from before. We found nu1 0.07341. Okay, so which one is actually bigger? Obviously, nu2 is bigger. Nu2 is bigger, so that means the x coordinate becomes bigger. If the x coordinate becomes bigger, this line must be to the right. 122 must be to the right. Okay, so now we go back to this diagram and we know point number 2 must be to the right side of number 1. So you can draw a vertical line to make it really obvious. Number 2 is to the right side of number 1, and then you can connect 1 and 2. So that's the process 1 to 2 on this diagram. Alright, so we're done with the first diagram. And then we go to the second diagram, T versus nu. Okay, remember on T versus nu diagram, we have constant pressure lines. Do you remember how to sketch a constant pressure line? Yes. Curve down, go straight, and curve up. Curve up, straight, and then curve up. This is a constant pressure line. We probably want to have two of them. Which one should be P1 and which one should be P2? Same rule. The higher this line is, the higher the pressure it represents. P1 versus P2, which one is bigger? P1 is 40 bar, P2 is 15 bar, so P1 is bigger. Then top one is P1 and bottom one is P2. Okay, so now let's locate number 1. Where is number 1? We know number 1 must be on P1 line, and what's the face of number 1? Point number 1 must be superheated, so number 1 must be somewhere here. Okay, next one, let's locate number 2. How do we locate number 2? Number 2 must be on P2 line, and we know number 2 is superheated. And one more, what do we know? 122 must be to the right. Okay, so 122 to the right. So number 2 also a superheated water vapor. Okay, so now that's the second diagram. Alright, so now we've finished the diagrams for P versus nu and T versus nu. That's part 2. And then the last part is part 3. Look for the cross-sectional area of the exit A2. Okay, which equation do we actually have for A? There's one given condition that we haven't used. What is that? Mass flow rate. We haven't used mass flow rate and we're looking for area. What equation goes to your mind? Rho VA. Very good. Okay. To look for part 3, we start from mass flow rate. Mass flow rate is equal to rho VA. Because it doesn't matter which surface you look at, because mass flow rate is constant, so we're going to apply this equation to surface number 2 because we're looking for A2. So I want to have A2 show up in the equation. Oh wait, do we have mass flow rate? Yes, and do we have V2? V2 is given. And do we have rho 2? Not directly, but something very similar. What is that? In this class, we do not deal with rho. What do we deal with? The inverse of rho. The inverse of rho is called nu. So this equation becomes V2 A2 over nu 2. Okay, so we have V2 given. We have nu 2 right here, 0.1627. And then one equation with one unknown, which is A2. A2 is very easy to find. Okay, rearrange this equation. Move A2 to the left-hand side. A2 is equal to mass flow rate m dot times nu 2 over V2. Okay, we have everything in the right-hand side. Plug in the numbers. 2 times 0.1627 divided by V2, 665 meter per second SI unit. Solution is 4.89 times 10 to negative 4. Because I use SI unit in the calculation, so my solution must also have SI unit. The SI unit for area is meter square. That is the example.